All right, this is chapter 18, section G, understanding functions and their derivatives. There's actually no new mathematics in this section. We're just putting some ideas together and thinking about some new, more challenging question types. So first, a little recap. When we take the first derivative and we check its sign diagram, that tells us some information about the original function. If the first derivative is positive, that tells us that our function f of x is increasing. If our first derivative is negative, that tells us that our original function is decreasing. If our first derivative is equal to 0, that tells us that we have a stationary point. That means that our original graph has a horizontal tangent line. If the first derivative is 0 and changes sign on either side of that 0, that tells us that we have a maximum or a minimum. Changing from plus to minus tells us that we have a maximum. Changing from minus to plus tells us that we have a minimum. If the first derivative does not change sign on either side of a 0, that indicates that we have a stationary, since the first derivative is 0, a stationary point of inflection. The second derivative tells us about the shape of the original function. It tells us how that function is increasing or how that function is decreasing. When our second derivative is positive, our original function is concave up. When our second derivative is negative, our original function is concave down. When our second derivative equals 0 and changes sign on either side of that 0, then we have a point of inflection. It's where the concavity of the graph changes. We can use all of this information to work both forwards and backwards between graphs of these functions, the original, the derivative, and the second derivative. Consider these 4 sections of a graph, f of x, drawn in black. The 2 on the top are both increasing, so that means that their first derivatives are positive. However, they're increasing in different ways. The one on the left is concave up. It is increasing at an increasing rate as we move to the right along this section of graph here. Not only is the slope of the tangent line positive, but it's getting more and more positive as we go along. In this section over here, the slope is always positive, but it's getting less positive as we go. It is increasing at a decreasing rate. In the examples below, both of those functions are decreasing, so the first derivative must be negative. However, on the left, it is decreasing at an increasing rate, meaning that it's getting more and more and more negative. It is concave down, the second derivative must be negative. And the second one, second derivative is positive, it's concave up, it is decreasing at a decreasing rate. The slopes are always negative, but they're getting less and less negative. For those of you familiar with physics, you could consider these graphs as being examples of position over time. The graph on the top left has a velocity and acceleration, which are both positive. In the top right, we have a velocity that's positive, but an acceleration that's negative. Bottom left, both are negative. Bottom right, velocity is negative, acceleration is positive. If you're not familiar with physics, we're going to deal with all this in chapter 23, so don't worry. But if you're already used to thinking about these things, I always found it helpful to think about calculus and graphs in terms of physics, so perhaps you will too. Okay, so here's an example from our text. We've got a picture of f of x, and they want us to graph, sketch, on the same axes, f prime and f double prime. Both of the answers that I'm about to reveal are going to be on the same axes, but I want you to imagine going through this one graph at a time. So first, we would sketch f prime, and then we would look at that and then sketch f double prime, and then we can always check our work by comparing to the graphs that we've already drawn. So here's everything. The thought process, as they say here. We look at our original graph and we're like, well, it has a local min right here at A, which seems to be on the x-axis. We also have a horizontal tangent line here at C. So when we draw the first derivative, which is here in red, it should touch the x-axis at both a and c. At a, it's got to cross through the x-axis, and it's got to start negative and then go positive, because the slopes here at a are negative and then are positive. Whereas at point C, the slopes are positive and then they're positive again. So the y values of f prime should be above the x-axis to the left of C and above the x-axis to the right of C. C is going to be a stationary point of inflection. B looks like a non-stationary point of inflection, right? It's going from concave up to concave down. How is this relevant to our first derivative graph? Well, we know that at a point of inflection, our second derivative is going to be equal to 0. How does that tie back to the first derivative graph, though? Well, when the first derivative graph is equal to 0, that tells me that the original function should have a horizontal tangent line. Therefore, when the second derivative has a value of 0, the first derivative should have a horizontal tangent line. So B and C, as inflection points, correspond to zeros of the second derivative. Therefore, they should correspond to horizontal tangent lines of the first derivative. We kind of knew we had to have that at point C because we had to have y values on f prime that were above the x-axis and then touched it and then were above it again. But we're also going to have that at point B. Another way to think of that is at point B, this is kind of the steepest of all of the positive slopes. If we look in between A and C, there's positive slopes the whole way, but the steepest positive slope is happening at point B. That steepest positive slope should correspond to the highest y value, or a local maximum, on the graph of f prime. And so that's how we can get this graph of f prime. And then from there, we repeat the process to draw the graph of f double prime. Well, we know we have a maximum here and a minimum here, so those are going to correspond to zeros of f double prime. We know that the graph of f prime, its slope is increasing up until that maximum, so the y values of f double prime should be positive to the left of that 0. The slopes are negative in between the two zeros, so we should have negative y values, and then the slopes are positive beyond that. So we should, if we have any graph f of x, we should be able to comfortably sketch the first and the second derivative curves. It takes a little bit of practice, but I don't think that this should be too much of a challenge for you. Going in the opposite direction, I think will be a little bit tougher, but we can do it. So here is a graph of f prime. And before we get any pictures going, I need to call your attention to this phrase right here. Sketch a graph which could be y equals f of x. So there's not going to be one specific answer when we take a graph of f prime and try to graph f, or when we have a graph of f double prime and try to graph f prime or f. When we work in this direction, there are more than one possible answer. And that should make sense. I mean, if I had two functions, f of x, for example, 2x or 2x plus 1 or 2x really plus any constant c, we know that f prime is always going to be equal to 2. So if all I told you was that derivative 2, you wouldn't really know what the original function was. You would know it would have to be some line with a slope of 2, but you don't know which line it is. And that's going to be the case anytime we try to sketch a graph working in this direction, where we're doing a lower derivative of what we started with. So we're going to look at f prime. The first things that I would look at are its zeros. We've got a 0 here at -6, or a. We've got another one here at c, which I don't really know what value that is. And we've got another one over here at e, not sure what that is either. At a, the y values of the first derivative are changing from negative to positive. That means that the slope of my original function are changing from negative to positive. At this x value, my original function will have a minimum. At c, we'll have the opposite. It goes from positive y values to negative. So that means the slopes in the original are going to go from positive to negative. That's a maximum. Over here at E, we'll have another minimum. I then turn my attention to points B and D. This is a max and a min for f prime. That means they're going to correspond to values where the second derivative is equal to 0. So those will be inflection points on my original graph. But because these inflection points are not also zeros of the first derivative, that means that they must be non-stationary for the original graph. And then I just sketch something that matches all the stuff I just said. We get this curve here. But we could have taken this curve and shifted it up or down as far as we wanted in either direction, and it would still be a correct possible graph of f of x. It's really just the x values of all the important points that matters. We have no way of knowing for sure what the original f of x had as y values at this minimum, at this point of inflection, max, point of inflection, minimum, and so on. Now that was a lot, and you may want to go rewind and listen to that whole thought process again. But before you do, another thought is that if I were doing this for real, I would have included a second sign diagram. So we've got this sign diagram here for f prime, based on the graph that we can see. But I would have also included a sign diagram for f double prime, because it's pretty easy to generate, and that could help me to sketch my graph, instead of just having to keep the thoughts that I was saying out loud in my head. So remember now that the sign diagram for f double prime is based only on the slopes of f prime. So to the left of B, those slopes are all positive. In between B and D, the slopes are all negative. To the right of D, slopes are all positive again. And then I can combine that information about concavity of my original curve with the information in the sign diagram of f prime, which tells me about whether my original curve is increasing or decreasing, and then we can get our sketch going. So starting from the left, to the left of -6, since that's the smallest x value in either of these sign diagrams, I know that the function needs to be decreasing, but it also needs to be concave up, and I know what that shape looks like. So I draw that in until I get to -6, then I need to change. From -6 until, well, I don't want to just think until -1. I want to think from -6 until -4. The function is going to be increasing, but it's going to be still concave up. So I've got that shape. Then at -4 until -1, the function's increasing, but it's going to be concave down. And then at -1, I change again. From -1 until, what's the next number? It's D, which is around 2.5, whatever. It's going to be decreasing and concave down, so I draw that shape in. Then from that point until 5, it's still decreasing, but it's going to be concave up. And then finally, to the right of 5, it's increasing and concave up. That's all there is for this section. There have been examples in the past of the IB asking candidates to draw sketches of whatever function based on whatever derivative. Sometimes you've got f prime and you're asked to draw both f and f double prime. Sometimes you're given f double prime, you've got to sketch f. Whatever it is, you should be able to do it. If you're studying for AP, I think this is even more common of a question type there, so definitely know it for that. It's not the easiest thing, but if you just consider the sign diagrams and are very careful, pay attention to your intervals, it's very doable. And I don't know, I think it's kind of fun and interesting. I mean, not that graphing a sketch of a curve is important as like a life skill, but I do think it's kind of cool that I can now take any, I don't want to say any function, but I can take a wide variety of crazy functions, and just by doing a little bit of calculus, I can get a really good sketch by hand of what that function looks like. And that's something that you couldn't previously do before this chapter. You could only get so much information without calculus, to sketch a curve without using technology as a crutch, but now we can do pretty much anything that you could reasonably be asked to sketch, we can do. I mean, there's a whole world of crazy functions out there that we don't need to worry about. I've mentioned the Weierstrass function before. There's this thing called the gamma function. There's hyperbolic trigonometric functions. There's functions that are defined parametrically. There's functions that use polar coordinates instead of Cartesian coordinates. All sorts of stuff. But that's not what I'm talking about when I say reasonable, well-behaved functions that we should be able to sketch.